remind you or tell you about this applied category theory school. It is in Oxford. It's this July, I think something like 12th through 26th, but I could be wrong about those dates. That includes both a conference and a school. The school is by invitation only, but everyone can come to the conference. I think there'll be something like 20 students in the school who, from all over the world, who will do research with one of 5 researchers. I'll be one of them, and Brendan will be a TA. And so if you're interested in that, apply by January 30th. Yeah, and any questions before we start? I wanted to talk briefly about adjunctions. And I wanted to mention 2 other things. One is participation. So again, participation is 25% of your grade if you're here for a grade. So it's really useful to everyone, at least me and you, if you ask questions when you have them. Someone in the first class asked about, are these partitions, are they surjections up to isomorphism? And you might have thought like, oh, that's an interruption. But for me, it was actually really helpful because I was going to get to that later and realize that I hadn't said anything about it and like hit some kind of like, really bad feeling. But by that person asking me about it, I was able to kind of fold it into the lecture as I went. So if you can ask questions when you don't understand something, there's probably a typo or there's something that should be said more clearly, so it's definitely helpful. So that's one thing, participation. And another thing is, if you're interested in doing projects, there's various venues for that. There's Europe, the Europe program, undergraduate research opportunity program, and there's just kind of doing stuff, hanging out and doing math. And we're here to, we do research, so it's not like we can spend all of our time, and that would be research, but we can't spend all of our time doing particular projects necessarily, but we can guide them and we can help facilitate them. So let me know if you're interested in that.
We also have a weekly seminar on Thursdays.
That's right. We have a weekly seminar on Thursdays, and if you want to join the mailing list, talk to Brendan or me.
Yeah.
Okay, so adjunctions, these are also called Galois connections when they're between posets. But I just wanted to briefly say that you have 2 posets, P and Q. These are posets. You have 2 functors, or also called monotone maps. One that you might call L and one that you might call R. And then you have this symbol here. And that weird symbol, maybe you could write a less than or equal to. What it means is that you have this round trip. And so for all P in P, it says that if you start here, it's less than going in the round trip. P is less than R of L of P. Brendan gave 2 conditions yesterday that are different than these 2, but they're equivalent. And the other one is that if you start in Q and round trip it, it's less than if you just stayed there. So L of R of Q is less than Q. And when people see this definition, they think, well, that seems fine. I'm glad you told me about that. I mean, it doesn't look like it's going to really help you in your life. But what's interesting is that these come up, I guess you could say that's one of the surprising things in category theories, how often these come up. These give you things like all of the meets and joins that we talked about yesterday. Meets and joins, so examples, and I'm not going to explain this completely right now, but or even at all, but it'll be for the fun time. Come ask me how meets and joins, or products and co-products, products and unions. And so meets and joins includes max and min and LCM and GCD and stuff we did yesterday, but also like discrete topological spaces, which are kind of the most boring ones, maybe, but they're still very useful. There's free groups. There's the Grothendieck deconstruction. I guess Grothendieck was the first one. Grothendieck deconstruction, if you've heard of that. There's group rings. There's so many things that I'm just not even thinking of them all. So many things you've seen before: free groups, group rings. All of these guys, polynomial rings. You may have thought, what makes polynomial rings special? Well, they're They're the rings you get from sets when you have an adjunction. Every ring has an underlying set. So here's rings, here's sets. You can take the underlying set of a ring. If you go backwards and you have this adjunction, you'll get polynomial rings. So these are adjunctions from category theory, whereas this is an adjunction of posets. But as Brendan said, posets are kinds of categories. So like in chapter 1, we kind of do the most basic stuff. In chapter 2, which we start today, we add one layer. And we keep going, but we can see reflections of all sorts of stuff from mathematics back in this very low layer of posets. So all this kind of category theory, these are for categories, whereas the thing I told you about here was just for posets. But and Brendan mentioned other ones for posets, like that show up in complexity theory, etc. But the point is that adjunctions show up all over the place, and they're quite interesting, even though they seem strange at first. So I just wanted to kind of tell you that I think we talked about it a little bit less than we could have, just because we have so much to do. And so if you have questions about it, you're not alone. Come and talk to us.
David,
Yeah.
can you also make a comment about the adjoint functor theorem? Just because I stated it wrong yesterday.
Oh, you stated the adjoint. Okay, so the adjoint functor theorem set. You want me to give a statement?
Maybe people can look it up, but I forgot to include the condition that. So I said that the adjoint functor theorem says that a monotone map is a left adjoint if and only if it preserves joins. But you have to have joins to talk about preserving them. So I should have said that we're assuming that the preorders have joins. And likewise for the condition with right adjoints and meets.
Yeah, so there's something called the adjoint functor theorem, proved by Peter Fry, and it's in the book, and it's about how if a functor, what we call a monotone map is actually a kind of functor. If a functor or monotone map preserves joins, and this guy has all the joins, all possible joins, you can join any number of elements inside of P, and L preserves those, then L will automatically be a left adjoint. Okay, that's what Brendan was trying to say, or just said. Okay, so today we're talking, so yesterday and the day before we talked about posets. These are about order, and now we're talking about monoidal posets. And these are like order plus combining. It's kind of the least, so we're building up here, we're starting with not very much. And so now we just have two things, order and combining. And so the motivation for this is the motivation is what are called resource theories. And a resource theory is, well, resources are things that you have or could have. And these are questions of, can I make what I want from what I have? From what I have, okay. Now maybe this is like the central question of life or something. Like this is what we're always doing. And this is not going to solve the central question of life. We're not going to get you to always be able to tell whether you can make what you want from what you have. But we're going to give kind of a basic theory that starts you in that direction. And that's the notion of resource theories. So, so here's an example. Making lemon meringue pie. It's in the book, so it's not going to be very surprising. But okay, you have some things. You have prepared crust, lemon, butter, sugar, egg, and more sugar. And you have various things that you can do. I can make yolk and white, egg yolk and egg white from, if I have egg. And I can make lemon filling if I have lemon, butter, sugar, and yolk. And I can make an unbaked lemon pie if I have prepared crust, which I could have done some work over here to get prepared crust. If I have a prepared crust and lemon filling. And if I have meringue and unbaked lemon pie, I can make an unbaked lemon meringue pie. And then I can put this into an oven, cook. I can take an oven and this pie, and I'll get this or baked pie, and I'll get my oven back, which is really important. Yeah, people think that's called a durable good, I guess. And it's also kind of a catalyst. So this oven is a catalyst for pie, because you get your oven back. Okay, so this is a resource theory. The resource theory would be the grocery store, I guess, would be a big resource theory, because Whole Foods maybe will actually do these products. So what is the resource theory actually here? It's a certain symmetric monoidal poset. The poset has as its elements all of the different ingredients and all of the sums of ingredients. So one object in the poset is prepared crust, lemon, butter, sugar. And another object in the poset, or element of the poset, is lemon filling crust. And the order of the poset is whether one combined thing is less than another. So these are the order. These say that this plus this is less than this. And the monoid structure is being able to combine things. So let me try to make that formal. Actually, no. So before I make that formal, this is the motivation, is resource theories. And then tomorrow, Brendan will talk about enriched categories, where you use, if you have a monoidal category, you can use it to enrich some other category. And that kind of, you could think of that in terms of trying to get where you want to go. Or like you have, whether I can get what I want, we ask that question. There's also not only can I, which is a Boolean yes, no, and that'll be Boolean enriched categories, but how much does it cost to make what I have from what I want, or to get where I want to go from where I am. That is what's called cost enriched categories, or you can have, what are the set of ways that I can make what I want from what I have, and that'll be set enriched categories, because it's the set of ways. So can I is Boolean, how much does it cost is another monoidal category, and what are the set of ways to get what I want is a set enriched category, and those are called categories. And so Brendan will talk tomorrow about enriched categories. They kind of structure this question. How can I, what are the ways that I can, blah, blah, blah. That's tomorrow. Any questions? Yes?
You said combining. How is that different from having a power set of just all the things you
Maybe you need 2 butters or 2 sugars, I guess. Right, yeah, so that's a good question. The monoid operation could be, the elements of the thing could be the power set of something, and then the operation could be union, but it could also be disjoint union. Actually, so there is a monoidal category where the objects are subsets and the monoidal product is union. So I will say everything I just said much more carefully in a second, but you're right, that would work fine. Other questions? Okay. Okay, so so maybe I'll just have you briefly recall and discuss with a neighbor for a minute or two what a poset is, what are the axioms of a poset, and what a Hasse diagram is, and how Hasse diagrams and posets are related. So why don't you just take a minute or two, make sure you remember what a poset is, and then we'll get going. Talk to a neighbor.
Yeah, totally.
Yeah, do you want to put this chair? Is that the car for you? Oh, there's a chair here if you want to put it on the chair.
You want me to move there?
And it makes sense that you can have things that
So I'm just looking for a break back.
Okay, okay, so I wrap that up. Okay, any last idea, anything, any questions come up for you? Everything okay? Okay, great. So let me define for you, let me define something called a monoidal set. Now you'll never see the word monoidal set in a category theory book. You'll see the word monoid. And you could actually find this in an algebra textbook. But a monoidal set consists of one, a set, say M, two, a function star taking M cross M, the product set M times M of all tuples M1 comma M2, and for every pair of M's gives you a new M. And this symbol is just a symbol. It doesn't mean times. It just means symbol. Okay, and an element, often called E in M. And this is called the monoidal product, or the monoid product. I say monoidal product. And this one is called the monoidal unit. This element. And they have to satisfy one, I, that A times B times C is A times B times C. So associativity. And II, that A star E is A, and that's also equal to E star A. Okay. So some examples of this are like the natural numbers examples. The natural numbers with 0 and plus. I guess plus and 0. So this tuple, 1, 2, 3, is an example. Another example is the natural numbers with times and 1. Another one is the natural numbers with exponentiation and 0. That's right, that's not true. Okay, this one's not true. In fact, there's nothing you can put here that'll make this true because it fails associativity. 3 to the 5, all to the 2. Why did I do that? 2 to the 3 to the 2, hopefully this will work, is not the same thing as 2 to the 3 to the 2.
Not equals.
Thank you. Okay, so these are monoidal sets. And a monoidal poset why does this sound different? That's weird. Okay, monoidal poset is a poset M. A poset M. Monoidal, well, I don't have to cross it out. A monoidal function, that's what? A monotone function. So that preserves the less than, and an element, and then this. So it's exactly the same. Well, it's not exactly the same. It's a monoid object in poset instead of a monoid object in set. But I'm not going to tell you what that means. That just means that in category theory, if you have a category with products, and you can define a monoidal blah, or if you have any monoidal category, you can define a monoid in it. And there's kind of this recursive thing where the fact that I could do this so easily, you can do that throughout category theory by just plugging any category with products in here, whether it's the category of sets or the category of posets. You don't know what categories are yet, we haven't told you. You don't know what products in the category are, unless you do. But the fact is that this ability to do this is something that category theory is trying to organize for you and let you do this automatically. Yeah?
What is the order on M cross N?
Good question. So in M, so if M less than is a poset, then the product poset is M times M with less than and less than. You might call it, I guess. So when is a tuple M1, M2 less than and less than? Let's call it less than. Less than M1 prime, M2 prime in M times M. Well, that's true if and only if, or you define it to be, that M1 is less than M1 prime and M2 is less than M2 prime. So this condition condition 2 says, condition 2 says 2 actually requires something of your monoidal set to be a monoidal poset. It requires that if M1 is less than M1 prime and M2 is less than M2 prime, then M1 times M2 should be less than M1 prime times M2 prime. So let's try to think of some examples of monoidal posets and some non-examples. So why don't you guys, in pairs again, answer this question. Which of these is a monoidal poset? So you could try natural numbers with less than, where the monoidal product is plus, and the monoidal unit is 0. You can try the reals with less than and times and 1, and you can try the reals with less than and plus. I just do it in order, plus and 0, 1 and times. Okay, yeah, which of these is a monoidal poset? Which of these is and isn't what?
Did you mean times and 1 or 1 and times?
Times and 1. Times and 1. Which of these is a monoidal poset? Thank you. So discuss with your neighbor. Are they all monoidal posets? First two.
But do we also have this?
So,
Which means
given that data. So then, the first one is M, the second one is
guys look really puzzled.
the third one is the fourth one is number one is the So let's do the first one. We check for the natural number, I meant that there's some A plus is equal to so next we need to check that a number A plus 0 something and that 0 and lastly can you need to make this condition which is to double check that this operation which takes two natural numbers is monoidal.
Okay, I kind of added a few, but does anyone have any comments or answers to this? Okay, the first row we have someone says yes, yes, no. Any other comments? Do you guys agree that this is a yes and a no? So what's the no of number 3? Yeah.
multiplication in the reals is not monotone?
That's right. Multiplication to the reals is not monotone because negative numbers don't satisfy this. Maybe when I was even writing this, you're like, wait, that sounds bad. That's going to be bad. But that's not bad for this one, or maybe other ones.
Well, it is for natural.
Because, yeah. Negative 1 is, so if you take negative 1, negative 1, 0, negative 1, and 0, you'll see the problem. Other question, or other, so I'm going to agree, yes, yes, no. And on the bottom row, which are new, yes and yes, or yes and yes. Yeah. So there's a lot of yes. Okay, any questions about monoidal posets? They come up a lot. I mean, you see them. What category theory is doing is taking things you've already seen lots of times in your life and telling you there's a name for the fact about how these are working and for the failure of this one to kind of know. This is a perfectly good, I mean, R with less than is a perfectly good poset. R times when 1 is a perfectly good monoidal set. But this altogether is not a perfectly good monoidal poset. Yeah?
How about multiplicative n?
Multiplicative n is here. Sorry, it's small. Is it small?
I was thinking R, yeah.
Okay. Yeah, multiplicative n is fine. The natural numbers with division and plus or times. One of those works, the other doesn't. Okay, let's go on. Oh, but just as an aside, we talked about monoidal sets and monoidal posets, but you could also talk about monoidal spaces, monoidal topological spaces, for example, or monoidal manifolds. And those are called Lie groups. Well, those would be called Lie monoids, but if they were groups instead of monoids. They're very similar to Lie theory. I mean, not to say that everything in Lie theory is covered by that, not at all, but that's what a Lie group is kind of a monoidal space. A monoidal category is something we'll talk about a lot. Seems to be kind of at the heart of applied category theory. And monoidal abelian groups, if I replace set or poset with abelian group there, a monoidal abelian group is called a ring. So these things come up all over the place. They're just organized into a structure that you get to see over and over. Okay, so the next thing I want to talk about is wiring diagrams, also called string diagrams. There's a subtle difference, but I'm not going to explain it today. If you're interested, just come up and ask afterwards. And what these are for is, what's the slogan of wiring diagrams or string diagrams? It's basically that you're involving the human visual cortex. That's like their selling point when they went to the investor. So I'm like, I have a company now, so I go to investors and I just have a selling point. It's really hard to, coming from math, to have like this. We don't come up with hard-hitting selling points, and this is the best I can come up with for the wiring diagrams. But basically, when you look at this, your visual cortex is like interpreting those as symbols. But when you look at this, it's easier to see kind of what this whole structure is. So there's various, yeah, so that's what wiring diagrams are for. And for example, Bob Cook at Oxford, who's kind of sponsoring this applied category theory school or hosting it, he has a book about quantum pictorialism, where he says that he thinks that the pictures of quantum processes, pictures of teleportation or measuring or whatever, all these quantum processes, they're closer to what's actually going on than the Hilbert space formalism. The Hilbert space formalism is how you test things. It's a way that it's what the diagrams can mean. But he thinks that, or he seems to say that, well, actually he wants to pit some 10-year-olds who learn his theory against some, he gets to spend 8 hours with them, and then the Oxford people that the Oxford students get to learn the Hilbert space formalism, and then they take the same test in each of their own language, and he thinks that the 10-year-olds will beat the will be the odd-sort people. So anyway, so wiring diagrams make things easier on you because you have this very developed visual cortex. Like that. Okay. So there are various flavors of wiring diagram, depending on whether you're talking about monoidal category or category. So in a category, and we haven't said what a category is yet, but we'll see things that look like this. In a monoidal category, we don't just have serial things, we have parallel also. So this is monoidal category, and today we're talking about monoidal posets, which is why we've seen pictures that look like that over there. In what's called a traced monoidal category, like vector spaces, there is something called trace, where you can take one of these pictures and you can do feedback. So in the category of dynamical systems, for example, there's feedback. In vector spaces, this is the trace of matrices. You take a matrix and you add up the diagonal entries, and that's what this symbol will symbolize there. And there's others too. I'm not going to say all the different flavors of wiring diagram, but they're kind of, well, I'll say one more, I guess. There's something called a hypergraph category, where you can have, where you don't really even think about what's in and what's out. And wires can split and all sorts of things. So there's hypergraph. In fact, relations form a hypergraph category. Vector spaces with bases form a hypergraph category. If you just keep track of the bases, you can form a hypergraph category. So these are all different flavors of wiring diagram corresponding to different flavors of, or what are called doctrines in category theory. Today we're just going to focus on this one. Okay. So if you were going to prove, okay, everyone get your proving hat on. If you're going to prove that 5.1 plus 7 plus 5.9 plus 2 plus 3 is less than 21 minus 0.5 plus 1.6 plus 1.6. And again, we're in day 3 of this class, so we're not proving really hard stuff yet. But if you're going to prove this to someone, you might notice that 5.1 plus 5.9 is easy. 5.1 and 7 and 5.9 and 2 and 3. And so since you know that those are easy, maybe you just add them first. Easy in the sense that you can add them first and get 11. 7 plus 2 is convenient because they're right next to each other, so let's add them. Maybe it would have been more convenient to add 7 and 3, but we didn't. And when you add these two, you see that it beats 21 and negative 0.5. And 3 beats 1.6 and 1.6. So this is the proof. And the proof is that all of these boxes are less than or equal to's, and every time we put wires next to each other, we're doing the monoidal operation. So whenever you have a monoidal poset, these diagrams that I said work for monoidal categories, they also, posets are categories, these diagrams will be unambiguously interpretable. So if you tell me what the operation is, then I'm going to use that to interpret what putting two wires next to each other in parallel means. And if you tell me what the less than operation is, that's going to tell me when I'm allowed to draw a box. And so now I know I'm allowed to draw a box in the places I have, and so now I've proven, if you agree with all these guys that they're true, then you've proven that the whole thing is true. And so a lot of times we do reasoning like this, like that's how if I was going to do some big operation, I would probably organize it in some way to make it easy for myself. But the point is, we don't want that to be cleverness that the human knows how to do. We want an artifact that we can hand someone that says, this is the calculation we did, so that they can tell us if they find an error, they can isolate that problem. So we're trying to kind of move things out of the realm of stuff that we're just special and know how to do, and make them things that we can record. So that's what this diagram does. Any questions about that? So this is the same thing as making meringue pie. to, well, not to cook, like, yeah, not to people who make meringue products, but to me, it's the same. Okay. Okay, so examples that you might have seen, examples from science. And they're not going to be that, let's see, how much time do I have? So, right. I guess what I just want to say is that you can find this stuff in chemistry. So in chemistry, is this called stoichiometry? I don't know if it's called stoichiometry. They might say things like, they might say that 2H2O, or H2O plus H2O, plus, what's happening? Plus 2Na, 2 sodiums, can turn into 2 sodium hydroxides and a H2. And if you replace this symbol with less than or equal to, and this is your monoidal product, then when you think of an operation or a, what do they call it? A chemical process where you have some kind of products and reactants, I think they're called, reactants and products, then that's kind of what, we could look at these same diagrams and just imagine like all of these filled in with these species of molecule. And when you have two species of molecule, when you have two different molecules, you can, they can turn into something else, et cetera, et cetera, et cetera. So if you know you can kind of follow some pathway through, then you can get from where you started to where you want to be. So that's kind of a very basic example where you've seen this before. They just use this symbol instead of less than. Actually, they add rates. They put rates on this stuff. And when you put rates on things, then it gets much more interesting, and then you can think about what are called Petri nets. And so if you want to learn more about like actually doing things with rates, you can kind of read John Baez's, people often say Baez, but it's Baez, and lots of other people. He's not the first, but he's the closest to me. So that's, so I think of him first. And he's very popular in terms of being well known. So that is what popular means. Petri nets, you can look at Baez to find out where to start to look at the whole literature on these kinds of things. So another example is for in manufacturing. You're manufacturing a pie, say, or you have hinges and nails and stuff, and you're making a door. But you're allowed to do something that you're not allowed to do in chemistry, which is you're allowed to throw things away. So when we made this lemon meringue filling, for example, we had a butter wrapper that we should have actually carried through, and will carry through for the rest of time until it gets used up by something else. And the separating the eggs and the white, we actually should have had an egg. We should have had a shell, and that would be carried through for the rest of time. And all of a sudden, our diagram would get very cluttered with things. So in manufacturing, I mean, when you make stuff, including pies, you assume that you can always waste or throw away anything you want. And obviously, we can see that that has both a savings and a detriment. I don't know what the opposite would be, but it's both good and bad, because we want to be able to throw things in the trash. I do it every day. But it doesn't always really mean what we think it means. It doesn't just go nowhere. But let's suppose for our thinking that we want to throw things in the trash. Then what we're actually saying is we're adding an axiom to our monoidal category, or our monoidal poset. We're adding the axiom, the waste axiom, the discard axiom. Let's put it here. This is not true for any old monoidal poset, but if your monoidal poset has the discard axiom, then it is true. And what is it? It says that for all A in M, A is less than E. So I can always take anything and get nothing. E is the monoidal unit, and I may not have mentioned it, but in these pictures, when you put two wires next to each other, I said that's the monoidal product. When you don't see any wire at all, there's a monoidal unit sitting there. So this is a monoidal unit. There's monoidal units everywhere. They're the ether of this. So if I had something and what I'm doing here is I'm saying, oh, I can throw away my butter wrapper. I've added the axiom that there's always a way of throwing everything away, and I just want to make that. I don't call it any. I want to make that so common that I just put an icon there, this dot icon that says, whenever you see this dot, it always means use the discard fact. Use the discard axiom. Any questions on discarding? Yeah.
So when you say that, when you're using the discard axiom, that means you're implicitly taking the monoidal product. So wait, well, like how does that let us do that? I guess.
The way that lets us do that is that we are able to write this when A plus B is less than C, right?
Mm-hmm. Oh.
We're also, but this implicitly is E plus A plus, right? And so now A is less than E. E is just the absence or ether of this world. So I write, so I don't know why, I didn't mean to switch to green, but denote this by, other questions?
It is a bit confusing. We can talk about it more afterwards, offline, or maybe I'll add something to the next problem sheet.
Which thing are you saying is confusing?
The fact that there's sort of an implicit monoidal unit lying around everywhere in these diagrams.
Yeah, these diagrams, interpreting them, yeah, exactly. Having a monoidal unit everywhere
Is it
takes some getting used to. What do you say?
Is it necessary to use the unit as the discard?
In the sense that I want to not draw anything to the right. I want to have nothing there, so that the other ones can be there unobstructed. E, when I add it to anything, doesn't change it. So that's why it's E. It's the monoidal unit because when I add it to this one, it doesn't change it. It's just this one. Makes sense. What was the question? Could it be something besides the monoidal unit that was there? Was that the question? Sorry. Right. If I called it something else, then I'd have a string. The fact that the monoidal unit is drawn as nothing makes it disappear.
So it's just a convention that.
It's a convention. Yeah.
But it's a convention permitted by the axioms. That
Other
make
questions?
it a sensible thing to do.
Okay. So in manufacturing, you might add this discard axiom, and in informatics, where you're working with information instead of things, you could add a. So we have manufacturing. Add discard. In informatics, where you're working with information, you not only can throw an email away, but you can also copy. So add copy. And copy says, the copy axiom says that for all A and M, A is less than A plus A. If I have A, then I can have two A's.
That's a star.
Yep. So if someone says, would you mind copying this CD for me? They don't mean copying the physical CD. It's not that you have a CD and now you have two CDs. That would be really special occasion. This is different. This is that you have a CD and you have, I guess in the book we call it a Beyonce CD, and you have a blank CD, and when you're done, you have two Beyonce CDs. Okay. But what we actually, that's what people mean when they say they're going to copy a CD. They don't mean copying the CD. But in information, if you have an email, so say you have a calendar, your calendar program is open, and what else do I need? Your Maps program is open. Then from that, maybe you've been able to use those to write your email. You've used them to decide how to write your email. And now you copy that email to several people. So, okay.
Do I still get to keep my calendar and my map?
Okay. Yeah, you can keep them.
But you can also discard information, I guess. That's
It's a good question.
what's going on in this.
Okay, so these would all be different flavors of monoidal category. I drew some pretty extreme different flavors where you're allowed to do feedback and you're allowed to not even know what direction means and things like that. But these are slightly less extreme. What they are is that they add just these two icons, the copy icon and the discard icon, to the monoidal category wiring diagram stuff. We're just allowed to use these if we add these axioms, discard and copy. Okay, questions about that? Okay, so in pure math, is it true that n union infinity with less than and infinity and min, that is monoidal poset? It's a monoidal poset because what this means is that this is the set we're going to use. Less than or equal to, you already know what it is, and you're not worried about whether 5 is less than infinity or not, you know. And this is the monoidal unit. When I min it with anything, I get back that thing. 5 and infinity is 5. Does this have copying? Does it have duplication? So this satisfies the copy axiom and the discard axiom. Someone says yes to discard because everything is less than the monoidal unit, E here. And what about copy?
Yeah. Everything is less than the minimum.
Yep, 5 is less than the min of 5 and 5. Because we're using min. So you could write a diagram. If you didn't know whether the minimum of 2 and 6, you're not sure, but you can prove that the minimum of 2 and 6 is less than the minimum of, let's see, what? Oh, right, 4 and 4. The minimum of 2 and 6 is less than the minimum of 4 and 4. And there's a proof. I don't know why they proved it that way, but that's their proof. Okay. Okay, so why don't you try to find a monoidal, so find with a partner a monoidal poset that, one, that does not satisfy discard, and 2, that does not satisfy copy, and 3, that does not satisfy either. So why don't you take the rest of the time and do that, and I'll call when time's up so you don't have to worry about it. Yeah, talk to a neighbor. Can you think of one?
All right. So,